Bernoulli's equation. Bernoulli's equation. For an ideal flow, no viscous force, P1 at one point, pressure at P1 plus half rho V1, the speed of the fluid square, plus rho g Y1, the location of V1, equal to P2 plus half rho V2 square plus rho g Y2. In other words, P plus half rho V square plus rho g Y is constant. I'm going to prove it later. If the speed of a fluid element increases as it travels along a horizontal streamline means y1 equal to y2, and the velocity speed, the pressure of the fluid must decrease. This increase, this decrease, okay? And conversely, Bernoulli's equation is strictly valid only to the extent that the flow is ideal. What is ideal? We mentioned 4 points. If the viscous forces are present, thermal energy will be involved. We take no account of this in the derivative of that follows. In the following deduction, we don't consider the viscous force. Okay? Now, we see this tube, the fluid flow from this side to swim. At the moment, say, we have a pressure P1, there's pressure P2, and there's a liquid press in, and this is out. Now let's see the situation, okay? This is where you want to find the proof, okay? How do we find it? You see, we see all this one, it goes up, it changes the velocity, it changes the potential energy of gravitational. What we do, we use delta K equal to W. The work done by these forces, P1, P2, gravitational force, equal to the kinetic energy change. What is the kinetic energy change? What is it? Half delta M V2 squared minus half delta M V1 squared. This is the mass M delta M. In, it is the mass out, okay? Inside the same, all right? This is constant. So we take the delta M out, and the delta M equal to rho delta V. That's the volume of this one. What's the W? We have two forces involved. One is the gravitational force, one is the pressure at the water. Let's see the gravitational force that equal to mgh minus. This is a gh, this is a potential energy of gravitational, minus is the work done by the gravitational force. This by definition, right? Yeah. With the pressure has a two. This is press in, this is press out. Okay, okay. This delta M is mu delta V, and W by the pressure is a two. Okay, okay. F2 x2 plus F1 x delta x1. Okay, this is positive. This is negative because F's go this way. So we get a minus P2 A2 delta x2 plus P1 A1 F1 delta x1. Now, W delta K, we put them together. Okay? Put them together. Half rho delta V G Y2 YC plus minus P2 plus V1 delta V equals delta K, half rho delta V equals C. And we cancel the delta V, and we find P1 plus half rho V1 squared plus rho Y1 equal to P2 plus half rho V2 squared plus rho G. That's the equation. We prove it.
As water flows through a tube, its pressure drops. If the tube has a constant diameter, the pressure drop increases regularly along the length of the tube. We'll use this device to show what happens when the diameter of the tube is not constant. Water flows through this horizontal glass tube, which has a large diameter at the beginning and end, but a constriction in the middle. The pressure in each of the sections is indicated by the water level in the vertical tubes. The two outer vertical tubes show the pressure drop that occurs along the horizontal tube. The center tube is covered. If the pressure drop was constant, we would expect this tube's level to be here. Will that be the actual height, or will it be higher or lower? The water level in the center tube is lower than expected, showing the lowered pressure in the constriction.
This glass pitot tube can be used to measure the velocity of an airstream flowing past. The pitot tube is a water manometer with two openings, one facing into the airstream and the other perpendicular to it. When air flows past the pitot tube, there is a difference in air pressure at the two openings, which causes a difference in water levels within the manometer. The difference in water levels depends on the speed of the air. When we increase the speed, the difference in water levels increases.
This device is known as a Flettner rotor. The rotor is a styrofoam cylinder powered by a small electric motor and mounted on a rolling car. When switched on, the rotor spins clockwise as seen from above. If we direct a stream of air from a fan at the rotor, the car moves perpendicular to the airflow. Reversing the direction of spin reverses the motion of the car. This animation shows how the moving air stream is deflected as it flows around the rotor, causing a reaction force which propels the car to the side.
A pitcher can make a baseball curve by applying the proper spin to the ball as it leaves her hand. We're going to increase the effect by using a light styrofoam ball and a throwing tube, which will put a fast spin on the ball. If the ball is thrown overhand as shown, so that it comes out spinning clockwise as seen by the camera, the ball curves upward. If the direction of spin is changed by throwing the ball side-armed, the ball curves away from the direction of the throw. This animation shows how the stream of air moving past the ball is deflected by the spinning of the ball.
If a jet of air from a blower is directed straight up, a styrofoam ball will float inside the jet. It stays there even if we tip the jet sideways, as long as we don't tip the jet too much.
If we blow air through the hole in the center of this disc, light objects such as this streamer are blown away from the disc. If we put a second disc up to the first with the air blowing, what will happen? The second disc is pushed up against the first because the air moving between the disc is at a lower pressure than the air beneath the lower disc. Even if we attach a weight to the lower disc, it still hangs beneath the upper disc.
These two parallel plates swing freely on strings. If we blow air into the space between the plates swing together.
Sample. Ethanol density rho 791 kilogram per cubic meter flows smoothly through a horizontal pipe that tapers in cross-section area from A1 1.20 times 10 to the minus 3 square meter to A2 equal to half A1. The pressure difference delta P between the wide and the narrow section of the pipe is 4,120 Pascal. What is the volume flow rate out of the ethanol? What we want, we found this one. A1V1 or A2V2. Okay? Actually, we want to find, because we know the A, so we want the V1 or the V2. Okay? What we do, we use this Bernoulli equation. Okay? At two terminal. Okay? Two terminal. And you see the horizontal, like they are horizontal, so H1 equal to H2, they cancel out. Okay? So delta P equal to half P1 minus P2 equal to half rho V2 squared minus half rho V2. Okay? And we know it's given 4,120 Pascal. Okay? And also we have A1 V1 equal to A2 V2. So these two equations, basically we can find the V. Okay, we'll put it inside, we'll find the V. Once we find the V, we can get the rho. So this is the V1, which is the AO, we get the VO. Sample. In the Old West, a desperate fires a bullet into an open water tank because water is so crucial for the desert, okay, at West. Okay. Create a hole, okay, a distance h below the water surface. What is the speed v of the water emerging from the hole? Now, this is we use the Bernoulli equation. We see the AV equal to AV0. Okay? And then we know the V0, okay, should be much, much smaller than V. And then we use the Bernoulli equation. Suppose this is a y equal to 0. So this surface y equal to h. So we had a P0 have the rho V0 plus h. This is 0. Okay? This is a P0 atmosphere. So they cancel out. And we get V about square root 2gh like the